Hi everyone, and welcome to our weekly wrap-up video, this one covering Module 2. We're very happy that so many of you are engaged in the course and lots of wonderful questions and commentary, and that's exactly what we want to see, and I hope you're learning a lot about the nature of reality and what science can tell about it. Now I have to do that in Portuguese. Olá pessoal, bem-vindos ao vídeo número 2 do módulo 2 do nosso curso. Nós estamos muito felizes com a atividade de vocês todos. Eu queria só fazer um comentário que é importante para vocês do Brasil. Vocês podem comentar o que outros escrevem, então vocês podem ter um debate entre vocês mesmos. A gente percebeu que muitos temas das discussões são uma pessoa falando uma coisa, a outra pessoa falando outra, em vez de ter uma troca mais ativa. Então a gente recomenda que vocês se engajem uns com os outros para poder aprender também e trocar ideias, ok? Bom, então vamos lá. Como vocês sabem, o vídeo é sempre em inglês nesse caso. Okay, so lots to talk about in week 2, module 2. I mean, big science questions. So we broke it down into about 4 big items, okay? And the first one, of course, is what is light, right? And some of you had these great ideas of asking people with different ages, about what is light. And somebody said, well, light is what is bright. And then the other one says, light is the opposite of darkness. And another one says, and there was this great quote from a 13-year-old that said that light emanates from something energetic and hot, like a star or a stove. And that is right on. Light is a sort of emanation, if you want to think of it that way. The only commentary here is that what this person is referring to is what we will call visible light, right? And there's also invisible light, that is light that our eyes cannot see. So for example, right now, Michelle is emanating in infrared, but I can't see that because my eyes cannot capture infrared, but she is hopefully at a 98.6 degree temperature, and then there is a radiation that comes out of a body at 98.6 Fahrenheit, and she's glowing in infrared. And so there are lights, there are visible lights, there are not visible, and we talked about the differences between them. And I want to re-emphasize that in a second, but before we do that, I want to put Michelle on the spot. And as you guys know, she is a PhD student in theoretical physics with me. And I want to ask her, as a scientist, as a physicist in particular, what does she think light is?
So I'll give the physicist answer and say light is an electromagnetic wave. I guess visible light has frequencies in a portion of the spectrum that are visible to our eyes, but you could also have invisible light, X-rays, infrared, things like this. And I guess light is also particles, photons, what we call them, and depending on what experiment we do, we can see either the wave-like properties of light or the particle-like properties.
Perfect. So light is not one thing. Light is many things, and it really depends on how we perceive it and how we interact with it. So she mentioned something very important, which is visible light is light of a certain frequency. So what does that mean? Well, if you think of light as a wave, okay, so a wave is something that you can draw like this, and there is a distance between two crests. This distance between two crests is what we call the wavelength. Okay, and different waves can have different wavelengths. So for example, let's pretend that this is red light so that you can see. So if you had light like this, so look at that. That one has a much shorter wavelength, and this could be, for example, ultraviolet light or X-rays. And those are also electromagnetic waves, but you just can't see them. Also, you could have something on the other one. You can have something with very big wavelength like this, which will also not be visible to us, as, for example, the infrared that is coming off Michelle here, and me too, and you too, by the way. But radio waves and microwaves, though these are waves that have bigger wavelength. So it all depends on this wavelength. And we talked about frequency. So what is frequency? Frequency is sort of like the inbuilt clock of a wave. So if you mark a certain spot, so I'm marking this spot, and you say, how many crests per second pass by that spot? If you have 1 crest per second, that means that this frequency is 1 cycle per second. That is called a hertz. So that will be 1 hertz. So if somebody talks about, hey, I have a 1 hertz wave, that means that there is 1 crest per second. If you have a 60 hertz, it means that in 1 second, you have 60 cycles, 60 crests passing by that point, right? And so visible light has nanometer wavelengths, roughly, 500 or so nanometer waves, and they'll have very, very high frequencies, okay? So that is, in a nutshell, the wave behavior of light. But of course, as Michel said, you can also have what is called the particle interpretation. And instead of having these waves, we're going to have photons. Now, we haven't really talked about it in Module 2, but we will in Module 3 and Module 4 when we talk about quantum physics, quantum mechanics. So you guys that have started Module 3, you know what's going on. You can actually talk about light as little bullets, right? And these little bullets are moving with the speed of light, and they're called photons, right? And these photons were proposed by Einstein in 1905, the same year that he talks about his theory of relativity, the special theory of relativity. So the point is that really depends. And of course, there is also the other kinds of lights, right? We can talk about the poetic way of representing light. You can talk about light as a metaphor for life, as opposed to darkness and death. So there are many layers in which we can discuss light. And of course, here we are focusing more on the scientific and philosophical aspects of light. But it's very important to remember that there are many discussions that you can have about what is light, okay? And we are going to keep going and exploring different kinds of ways of thinking about light as we move on. Of course, in astronomy, why is light so important in astronomy?
Well, it's one of the only things that we can see from the galaxies and things that are very far away from us. We collect their light so we can learn about what's going on.
And what kinds of light you can?
All kinds of light. We collect the visible light, we collect X-rays, we collect infrared light, radio waves, anything we can to tell us all about the different sorts of properties and things that are happening in the universe.
So what Michel is saying is really important, that astronomy now is not just about the little romantic guy with a telescope looking at a shiny planet or star. It's actually about any kind of light. Everything emanates in different wavelengths. So you can have a star that is shining at a certain color. For example, you can have a red giant star, so it has mostly red color, but it also emits radiation in infrared, in ultraviolet. So there are telescopes that can capture infrared, ultraviolet, radio waves, and they're all important because they give you a sort of a complete picture of what's going on with that stellar or celestial object in general. So astronomy needs all of those things, right? Which brings us to relativity. So what's the essential relationship? Where does light come in the theory of relativity?
Well, the speed of light is a constant for all observers in all reference frames, and that was the assumption that gave birth to relativity.
Right.
Or the
Which is
observation.
super counterintuitive. It's just weird stuff, right? You don't expect that to be true because you know that usually you talk about relative velocities, right? So if you're walking and you throw a ball, the ball is going to have a certain speed for you, but if the person is standing and seeing you walk, the velocity of that ball for that person is going to be the velocity that you're walking plus the velocity of the ball. So the two of them. Light is not like that. It always has the same speed, which in empty space is 186,000 miles per second, or in grown-up units, 300,000 kilometers per second, which is a ridiculous speed. I mean, if you blink your eye, light goes 7.5 times around the Earth, which is like crazy, right? Blink, 7.5 times around the Earth, and it takes about 8 minutes, right, for light to come from the sun to the earth. So when you look at the sky and you're looking at the sun, you don't see the sun as it is now. You see the sun as it was 8 minutes ago. So if the sun exploded right now, we would not know that and for eight minutes until, that whole thing comes in. And of course, that'll be the last thing we'll ever know. Boom, end of Earth. But the point is that the information that astronomy is capturing from the sky through light, it's delayed information, because even though light is super fast, it still takes a while for it to go from point A to us. So when you look at the night sky, you're actually looking at the past. So in a sense, the night sky is kind of like a time machine, because you're looking back, right? So Einstein had this thing about the special theory of relativity, where he showed that the speed of light, even though people talk about the theory of relativity, the theory is actually about absolutes. Two absolutes. They're called the postulates of relativity. The first one being that all laws of nature are the same, irrespective of how observers are moving in relation to one another at constant speeds. That's why it's called the special theory of relativity. Everything is at constant speeds. The second postulate is that the speed of light is the speed of light, is the speed of light. It never changes. So the theory of relativity is based on actually two absolutes, and people sort of lose sight of that, but that is extremely important, right? And then, of course, Einstein knew that constant speeds are kind of a fabrication. Mostly you move at accelerated speeds. You have to stop and move, and to do that, you have to change your speed. So he wanted a more general theory, and that's the general theory of relativity, which has at its core idea
geometry
and the effect of
gravity.
Yeah, and the matter bends geometry, right? So it was this beautiful connection of energy, because E equals mc squared, so matter and energy are kind of undifferentiated in a sense. So you have that you can actually bend space. So the typical picture people make, which is not a very precise picture, right? But it's the idea that if you have a plane, right, and this thing is flat, if you instead have a mass under it, let's say, and apologies for the artistic, endowment here is not the greatest, that this is going to bend, right? So you're going to, if you're looking at it sideways, you're not going to see a straight line anymore. You're going to see something that is going to go like this, and the mass is what's making this space bend, right? So Einstein realized that if you wanted to explain gravity, you didn't really need to talk about this mysterious action at a distance that Newton talked about, was sort of like an instantaneous thing between, say, the sun and the earth, but you could actually just talk about the bending of space around a material object. And you know what? You guys are bending space around yourselves. We are bending space around ourselves. Fortunately, gravity is a very weak force, otherwise we'll be all bundled up, on top of each other. That doesn't happen. But when you have a very massive object, you do that. And of course, as you remember in the video, you can show that there are different orbits that you can have because of this bent space, right? What Einstein's insight was that acceleration can mimic gravity. That's the principle of equivalence, which is the core idea in general theory of relativity, that if you are locked in an elevator and let's say you're going up very fast, you feel heavier. The heck happened, right? I mean, you're not gaining weight because you're in an elevator going up. What's happening is that the acceleration of the elevator is giving you this feeling of becoming more massive, more gravity is stronger. So you cannot actually separate the two. One can mimic the other. And that's the real insight of general relativity. And then, of course, that takes us to our third point today, which is the notion of cosmology. Because Einstein had this great thing, and in fact, we should be celebrating because he wrote his paper on cosmology in 1917. So 100 years of modern cosmology started, so here we go. And by the way, the course ends on March 14th, which is Einstein's birthday. A happy coincidence, or is it? And we should also mention that if by any chance you have not started doing the course-related work, you don't need to panic. You can start at any time as long as you finish by March 17th, which is when we're going to close the books on all this work, right? So you can do it, you can binge the course, you know, like 2 days, do everything, March 15th if you want, or celebrate Einstein's birthday, doing everything on the same day, March 14th, just go for the whole thing. So it's okay to do it as long as you finish by March 17th, right? So Einstein said, hey, since matter bends space, if I know all the matter in the universe, I can actually come up with the shape of the universe itself. Now that's pretty powerful stuff, right? I mean, can you imagine you write an equation on a piece of paper and out comes the universe? That's pretty amazing, right? That's the power of mathematics and theoretical physics. So Einstein said, how can I do this? You know, my equations, basically Einstein's equations are sort of like this. Geometry equals energy. What that means essentially is that energy / matter tells me what the geometry of space is. And space is really space-time because space and time are mashed up in gravity, right? So basically solving Einstein's equations means give me an energy source like a star, a planet, a person, and I'll tell you what is the geometry of the space around that object is. That's the idea. So he says, hey, give me all the matter in the universe and I'll know what the geometry is. So he made a simplifying assumption. He says, let's assume my space is the most perfect possible, a sphere, okay, with a radius like this. And the matter in this space, you have to remember something very important. I can't draw a three-dimensional sphere, so I'm drawing here a two-dimensional sphere. You have to imagine that the stuff is on the surface of the sphere, so the little dots here are on the surface of the sphere, like the galaxies and stuff, for example, right? So you live in a two-dimensional sphere, or if you want to think of a flat space, imagine the flat surface of a table. You are this little amoeba moving on the top of that surface, and that is your two-dimensional universe. No north, south, east, west, no up and down. Anyway, so Einstein said, let's assume space is static, so it's not moving in time, and it has a finite size. And let's assume that the energy, the matter in the universe is distributed the same way everywhere. So that's called the cosmological principle, right? So what does that mean, more or less, the cosmological principle?
It means that there's no really special place in the universe. Just everything is the same in all the directions everywhere.
Yeah, that's exactly right. So it's the fancy way of saying that so you can impress your friends in a party is to say, you know what? The universe is homogeneous and isotropic, which basically means that everywhere you look, it's the same, and in every direction, it's the same. If you look at very large distances. Of course, you know, if I'm looking up and say, but that's Orion is not the same as, you know, Cassiopeia or something like that. These are different things, yes, but you have to take a big chunk of space, average over all that chunk of space, and then you look at another chunk of space, and those two big chunks, we're talking about tens of millions of light years, then that's where the universe starts to look similar, okay? And that's the cosmological principle. Another way of thinking about that, as we did in the course, right, in the video, is you put a bunch of stuff in a blender, right, and you have the little chunky things, but then you blend them all, and you have a soup, which is homogeneous. That's the idea. Imagine everything is spread about. So he did this, and then he solved his equations, and he found a solution. Hey, the universe is a certain size. But then he looked at how stable that solution was, and you know what happened? His universe was unstable and started to collapse. And he hated that. So I don't want an unstable universe because clearly we're here. So he put in by hand something which is called
the cosmological constant.
The cosmological constant, which, you know, it was sort of a fudge factor really to make sure everything was there and stay there. It was kind of like a repulsive force, not for matter, but for space itself. Because remember, now we're talking about space being plastic, you know, having this stretchiness factor. So The cosmological constant is something that makes space stretch out, but then matter makes space contract, and between the two you find a balance. That was the idea, as long as lambda is related to the size of the universe and how much matter there is in there. So that was Einstein, 1917. That started modern cosmology. 5 years later, people said, but hey, take that out. And now you have a universe that can expand and contract, you know, on paper. And then 1929, the American astronomer Hubble comes with his expanding universe idea that actually galaxies seem to be moving away from one another. So let's take a look at that. And that is the expansion of the universe, right? So let's draw here the universe in 3 snapshots in time. Okay, early on, a little smaller, and you have, say, 4 galaxies. Each one of these dots a galaxy. Then time passes, a little bigger, and those galaxies are moving out. And then time passes some more, a little bigger, galaxies are moving out like that. Now let's imagine that this galaxy here is our galaxy, the Milky Way. So you look out and you say, haha, look at that. That galaxy is moving away from me. That galaxy is moving away from me. Look at that. The distances are getting smaller, larger and larger. As time advances, time is going this way, right? So you say, I am the center of the universe. Look at it. Everybody's moving away from me. I'm really important. But then you get a radio message from the folks on the other galaxy that takes a few million years, but forget about that. And they're going to say, no, wait, I can see everybody moving away from me, right? And then the other galaxies agree, no, I can see it too, so I'm the center. No, I'm the center. Well, the story here is that there is no center. Because of the cosmological principle, every point is essentially as important as another point. And so this circle of influence here, which grows, as time goes by, is what we call and define as the cosmic horizon. Well, each one of these galaxies is going to have its own cosmic horizon, okay, which is the distance light has traveled since the beginning of time. Because if you go backwards here, you're going to go to a time when things were tiny, right? And that's where we get to the Big Bang, right? Which is a terrible name, really, because the Big Bang sounds like an explosion. So can you see what the problem is? That people say, oh, the Big Bang, yes, everything has a little point, right? And then boom, it explodes, and galaxies are like the shrapnel, kind of this bomb exploding. Can you catch what's wrong with that picture that people have, that they always think that way?
Well, it's not really an explosion like, boom, out come the galaxies. It's really just that the whole universe is expanding itself. It's not little pieces flying out of this chunk.
Right. So the fundamental error that people make when they say the Big Bang was a big explosion, from the center and everything, that view is the view where space is static. That means that a bomb explodes and things move in space, but space is not changing, right? While the Big Bang, the expansion of the universe, is an expansion of the space itself. So the galaxies are basically taking a hike. They're taking a ride with the expansion of the universe, kind of like a surfer that is moving along the wave. And that is the idea. So the galaxies are actually being carried along the extractionness of space. And it's not that space is static, like the stage where the bomb explodes. And that is where it's hard for people to understand the difference between what's the real meaning of the Big Bang and this explosion thing. I hope that clarifies that. That's a point that comes up on and on, when we talk about these things. And finally, we have one more thing to talk about, the multiverse. The famous and infamous, depending who you talk to, multiverse, right? So, Michelle, do you have any interesting comments on the multiverse, questions that you may have about the multiverse?
I guess I would like to, a lot of people were talking about, is this multiverse idea, is this really science? Is this really testable? And I kind of like to hear your perspective on what the state of the science is. And
right. So, of course, those of you who are smart enough to read my book, plug, would know in much more detail than what I can tell you in a couple of minutes. But the essential point is that the modern theories of physics, especially high-energy physics and cosmology, right, the beginning of the universe, they naturally ask for something like the multiverse. They make it plausible. Now, the idea here is that the multiverse is a collection of different universes. So you could imagine, that there is this big entity in space where, once in a while there'll be like little dips. We call it the landscape. And each one of these little dips is going to be a different kind of universe with different kinds of, not laws of physics necessarily, but different constants of nature. So what the heck does that mean? Well, a constant of nature is essentially something that defines the forces and the properties of particles. So for example, the fact that I mentioned that gravity is weak is because there is a constant, which is called Newton's constant, that defines the strength of the gravitational force, which is a measured thing. You go to the laboratory, you measure that thing. It was measured by Cavendish a long time ago. So the electron has a charge, the proton has a charge. Those things are constants of nature. So what some theories of modern physics say, like string theory, or also the inflationary universe theory, which tells you that in the beginning the universe used to expand super fast, like an inflation in economics, right? And then it slowed down. And it turns out that those two theories, they sort of naturally predict that the universe could be partitioned into this multiverse where our universe would just be one guy out of an infinite, or not quite infinite, but very, very large ocean of possible universes. And it's plausible that in each one of these, the constants of nature, including the cosmological constant, by the way, would have a different value. Okay? So that's the idea behind the multiverse. Now, what is the problem? Well, there are many problems, okay? But the most essential problem is that if the multiverse is an abstraction, I mean, it's something that is being proposed because of certain theories that we do not know are right or wrong. So this is very interesting because it has to do with the notion of the limits of knowledge. So science at the fringe, right, at the edge, is speculative and often wrong. But we have to be daring. We have to try very hard to make sense of what's going on. The difficulty with the multiverse is that we don't have any data. We don't have observations that actually suggest that this idea is possible or even plausible. All we have are theories that if you extrapolate them a lot, you get to this notion of the multiverse. So a lot of physicists are very unhappy with the multiverse because the point is that if you live in this universe here, so let's say that this is us, we cannot have any information about our neighbors directly because they are outside our cosmic horizon. So imagine that you are in a bubble of information, which is the distance light traveled in 14 billion years. Those other universes are outside this bubble. We cannot get any information in the form of radiation or any other kind directly from that. So we'll never know for sure unless you violate the second postulate of relativity, that the speed of light is constant, that there may be other ways of traveling across space. We'll never know for sure if the multiverse is a reality. But Michelle is asking, is there anything else you can do? And if you watched my interview with Matt Kleben from New York University, so Matt is a cosmologist, and he is one of the fellows that proposed that if there are different universes out there, it is possible in the history of our universe, 14 billion years, that a neighboring universe sort of collided very gently with our universe, kind of like soap bubbles, you know. So imagine our universe is a soap bubble. Another one comes by and breezes through. Because if it's very violent, we wouldn't be here to tell the story. So it has to be sort of like a nice kind of passing by. And if that happens, so there's a little universe, it comes here, it sort of collides with our universe very gently, it will cause waves in the geometry of our universe that would propagate in time and would leave an imprint in the sky. Okay, and the imprint has a very specific signature, just sort of like concentric rings, you know. And Kleban and others proposed that you could look out in the so-called cosmic microwave background, which is this gas of photons that has been around for almost the beginning of the universe, you know, since we were younger than 1 billion years, and actually younger than 1 million years. So really, it's about 400,000 years after the Big Bang. And that thing would carry an imprint of this previous collision. So go out and look at the microwave background. People have been doing a lot with it. We'll talk more about it. And so far, nothing has been found, right? And the question then becomes, even if you find something, let's say somebody finds an imprint that looks a lot like what you would expect from this neighboring collision, can you tell then that this is a signature of a multiverse? Well, you can say that maybe if the signal is unique, right, because it could be something else that masks that signal. Now, Kleban and others would say, hey, it's a very unique signal, you can't mask it. But we don't know that, and that's the problem. Sometimes there are other ways of explaining the same thing, right? But even if you do that, and even if it is related to a neighboring collision, you can say, yeah, there may be another universe, but from there to a multiverse is a very big step, right? And there's also a philosophical perspective on this, which is if you can't determine if something is real, should it be part of science or not, right? And depends who you talk to. People can get very excited about this. Some would vehemently say, absolutely not. This is not science. This is not part of physics. This is something new that we never had to deal with before. A concept that cannot be tested should not be part of physics, period. I tend to sympathize with that idea. But then people say, for example, atoms. You know, atoms have been around for 2,000 years, you know, from the pre-Socratics, Lucretius, and we only found out about atoms for real in the early 1900s. So how do you deal with that? Well, it's very different because atoms were still part of our reality in a sense of they're small, so hard to see, but not impossible to see because they're far away due to the speed of light that you cannot. So there is a difference between atoms and the multiverse, and it is a very deep conceptual difference. And so others say it doesn't matter. You know, thinking about the multiverse opens different possibilities for theoretical physics, and that's all that matters. You know, it's inspiring people to think about different things. And I kind of like that too. It's true, as long as you don't take it very seriously. See, the danger is to make an idea into a reality before you can. And then take all sorts of crazy extrapolations, you know, about what is the multiverse and where is it and blah, 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 when we really don't have enough science to back it up. So I think that's it. Unless you have something else you wanted to touch on?
Yeah, I think that was a good wrap up, a good summary, and I also think that just having these ideas in science, these sort of crazy things, can help us better understand our own theories and the ones that eventually end up being right. So they have some value for us in learning about just what it is we're doing.
That's exactly right. So the multiverse may never be confirmed to be true, but it's a useful tool as long as we don't get too carried away and start writing books about, hey, the multiverse exists, you know, and it proves this and it proves that, when we don't have the foundations to do that. But it does increase the island of knowledge a little bit, even though, of course, as the island of knowledge grows, so will the shores of our ignorance. And in the case of the multiverse, it is an idea that brings out more questions than it actually solves. So I hope this wrap-up of Module 2 was useful to you guys as, as an aid to the course. Again, if you have questions, keep asking them. We'll try to summarize them in these weekly wrap-ups. And I also hope that you dive into Module 3 and then Module 4 when we start talking about matter and the mysteries of quantum physics, where things change quite dramatically, and you're going to see how the nature of reality is related to all of those questions. E pessoal do Brasil, espero que vocês tenham gostado desse vídeo de resumo do módulo 2. Espero que tenha sido útil também em termos pedagógicos. E agora a gente vai para o módulo 3, depois o módulo 4, em que a gente vai tratar do que é a matéria, dos mistérios da física quântica e como ela se relaciona com a natureza da realidade. See you guys next week and keep up the good work!